Howdy, folks. What I'm going to introduce to you now is a third kind of test. I know you're getting really tired of all these letter tests. First we learned how to do a Z test, then a T test, and now I'm going to introduce you to what is called the F test. Okay. Now the F test is kind of interesting. As we, the Z test was sort of straightforward. Once we got to the T test, it became a little more complicated because we added degrees of freedom. Well, here on the F test, it's going to become even more complicated because we have in the F test and the F table what is called degrees of freedom for the numerator, and then we have a completely different degrees of freedom for the denominator. And so what I'd like to do in just a minute is switch over to my computer so that I can show you how to read an F table. But here's an example. You can see here, we have numbers across the top, and then we have numbers across the side, and they're all degrees of freedom. And across the top are the degrees of freedom for the numerator, and across the side are the degrees of freedom for the denominator. Okay? Now the F test is popular for basically two kinds of tests that I'm going to show you. So we're going to do one of them today, and then we're going to do the other one in the next class. And that is today we're going to do a test where we compare the variances of two populations. And then in the next class, we're going to do an F test that is called ANOVA, where we compare the means of multiple populations. Okay, and usually the F test, especially when we do the ANOVA, we do most of the work on through Excel. We would do it on a computer. Where what we're going to learn today is we're going to be able to do everything just in a calculator. Okay. So what I'd like to do right now is we'll switch over and I will show you how to read an F table, and then we'll come back and then I'll show you how to do a hypothesis test for variance. Okay, so what we have here is this is an F table, and just like the Z table and the T table, we have to find something along the sides, and then we have to find something along the top, and then we have to kind of go in from, so let's say we have a 15 on the side, and we bring it over, and then we have a 10 along the top, so we come down, and so for example in this table, if we had a 10 on the top and a 15 on the side, our number would be right here, which is 2.54. Okay, and that would be our critical F value. That's the purpose of this table, is to give you a critical F value. Now let me show you a couple differences. There's two pages. There's this page, and if I scroll down, you can see that there's a second page. Now they both look very similar, but the numbers are actually different, because if I go down 10 and over 15 on this side of the table, the number is 3.80, which is very different than the 2.54 that we had on this side. Okay, so what's the difference between the two sides? Well, one side says F value for alpha 0.05, and that's when your P value is 0.05, and the other side is F values for alpha 0.01, that's when your P value is 0.01. And so you have to decide, okay, are you dealing with a 0.01 test or a 0.05 test? And whichever test you're doing, that's what side of the piece of paper you have to be on. That's the table that you have to be using. So then what are the numbers along the top and what are the numbers along the side? Well, those are the degrees of freedom of what we call the degrees of freedom of the numerator. So you see this D1, the numbers across the top, those are the degrees of freedom of the numerator, and then along the side is D2, those are the degrees of freedom of the denominator. And so all you have to know are the degrees of freedom of the numerator and the degrees of freedom of the denominator, and then the alpha level, and then you just bring them together and find your critical value in the middle of the table. Okay, and so if you knew that the degrees of freedom of the numerator were 24 and the degrees of freedom of the denominator were 18, then we would go to the 24 along the top and go down. And then if we knew it was a 0.01 test, we couldn't use this side because this is a 0.05. We would have to flip over to the next page to the 0.01 side, go to 24, go down along 24 to wherever 18 is, go over 18 to where 24 is, and this would be our critical value. Our critical F value would be 3. What is it? 3. Let's zoom in here. It's hard to see from here. Yeah, it's 3.00. Okay. Oh wait, no, 24. Here it is. Yeah, 3.00 would be our critical F value. Okay. And so that's how you read an F table. Very simple. Now what we're going to do is we're going to use this ability, and we're going to learn about another hypothesis test. All right, now that you know how to read an F table, we're now going to make use of the F table in what I'm going to call, or what can be called, a two-sample variance comparison test. What we're basically doing in here is the same thing that we did in a previous class where we compared the means of two samples. You may recall that we had done a test where our null hypothesis and our alternative hypothesis were the population mean of one population is equal to the population mean of another population, or the alternative hypothesis is that the mean of one population is not equal to the mean of the second population. Okay, so this was a two-sample hypothesis test where we were comparing the population means. But now what we're going to do is we're going to do the same thing, only now our comparison, instead of comparing the means of the two populations, we're going to compare the variances of the two populations. Now, before we do that, I need to remind you of what variance is. If you recall, standard deviation of a sample is given by the letter S, but the standard deviation of a population is given by the Greek letter sigma. And I also want to remind you that variance is standard deviation squared. So when you see S squared, that means variance. So when we see sigma squared, that also means variance. This S squared, that is the variance of the samples that of the sample that you have taken. Whereas sigma squared, that is the variance of the population. And in this hypothesis test, we are going to make a statement about the variances of two populations. But to test it, we're going to use the samples, the sample variances. Okay? So instead of comparing mean to mean, we're going to compare variance to variance. So instead of having mu sub A, we're going to have variance, sigma squared sub A. So that's the variance of population A. And the null hypothesis, our starting hypothesis, is that there is no difference. There's no difference between the variances. We are going to assume until we have statistical data, statistical evidence, until we have a reason to believe that their variances are different, we're going to assume that their variances are equal. That's the null hypothesis. The alternative hypothesis, what we are testing, is that the variance of population A is not equal to the variance of population B. Now, in this particular test, this F test that we're doing, we are only going to do a two-tailed test. We're not going to have a hypothesis where it's greater than or less than or anything. For this particular test, always your null hypothesis, and when I say always, I mean always for this class. When you get to intermediate statistics and you learn more about statistics, sure, you could do a test where you hypothesize that the variance is greater than or less than. But in this class, for my class, we are only going to do the case where the variance is either equal or not equal, which means automatically it's always going to be a two-tailed test, okay? Which means that we're always going to divide the alpha level by 2 to get our p-value. Now, one of the things that I mentioned in the video about the F, or about when I was on my computer, was I mentioned that we're only using, for this F table, because of how complicated it is, we're only going to be dealing with an alpha of 0.05 or an alpha of 0.01. because I have only provided you with the tables that include alpha 0.05 or alpha 0.01. Now this is going to be after we divide by 2. So really what we're going to deal with is we're going to deal with alpha of 0.10, because then when that's divided by 2, it's its p is 0.05, and then we're going to deal with alpha 0.02, and when that's divided by 2, because it's a two-tailed test, right? When 0.02 is divided by 2, it's going to be 0.01, and then you would use the table that says alpha equals 0.01, okay? Those are just technical details for now. And I think we're about ready to go ahead and jump in and learn how to do this test. So what I've done is I have provided you, I've created a problem, which I'm going to put up on I'm going to project it up here in just a minute. But I want to tell you that the very first step in doing one of these problems, the first thing that you want to do is calculate, using Excel, calculate the variance, the sample variance. Let's do that. Well, yeah, let's calculate the variance of both samples. Okay, so that is going to be your very first step. As soon as you get, you're looking at a question, you'll have a sample from 2 different populations, and the first thing you want to do is use Excel to calculate the variance of each one of those samples. And here's what's going to happen is the larger variance is the numerator, and then the smaller variance is the denominator every time. Okay? So let's go ahead and project the problem up here on the board, on the whiteboard. There we go. All right, so here's, hopefully you can see this okay. It says, determine whether the variances of the 2 populations, here they are, determine whether the variances of the 2 populations are significantly different, whoops, this is supposed to say, at the alpha equals 0.10. So I'm going to go change that right now. There we go. At the 0.10, alpha equals 0.10 level of significance, okay? So what you should do right now is you should go ahead and take this data, maybe you can pause the video, take this set of data and this set of data, and then put them into Excel and do descriptive statistics. Okay, and you may have to look back at another video. If you don't remember how to do descriptive statistics, you have to be able to identify the variance of that population and of that population. So if you got to go find out how to do that in Excel, you go do that. But here's what I need you to do. Before we do anything else, you need to identify the variance of population A and the variance of population B. Okay, so I'm going to go do that on the computer right now. All right, you can hear me, but I'm standing over by my computer. I'm going to take all this data and I'm going to enter. I'm going to put it in a column so that it's, oops, let's do that, so that it's up and down. There we go. All right, that's the first set. So population A, to find the variance, zoom out a little bit here. There we go. And I'm going to go to data analysis, and I'm going to choose descriptive statistics. I'm going to hit OK. My input range will be this set of data right here. I'll press enter. Then I'm going to go to output range, and I'll select an output. Let's say we'll put it right here. Enter, and we'll hit OK. I have to choose summary statistics. There we go. Hit OK, and let me open them up here. And let's see here. Let me increase the size of this. There we go. There's the variance. Sample variance. There it is. Okay. There's our sample variance, which is 77.983. 333. That's our sample variance right there. Okay? All right, so we have population A, the variance. Well, let's do this. S squared, the variance of population A, is 77.9833. So we'll stop there. Probably go, maybe we'll just do 3 decimal places instead of 2. Although, you know what, we're going to divide something, so let's actually go out to 4, 5, or 6. There we go. So there's the variance of population A. And now I'm going to delete this. Let's go back over here and we'll grab population B. All right. And there. I'm just trying to make them all vertical so that because you know I have to put them all in a single column before I can use the descriptive statistics. Almost there. X. There we go. And now let's go over here. And I'll widen this right here. There we go. And I'll go data analysis, descriptive statistics, and I will choose a new input range. Oops, here we go. Grab from here to here, press enter. I'll put my output right here, I suppose. That'll be good. Enter. And then summary statistics, and I'll hit OK. And then I'm going to make all these letters larger. And sure enough, there's the sample variance right there. And the variance for the second population, for population B, whoops, I erased it all. I can undo all that, is 197. So variance for population B here is 197.774891. 7748, well, maybe 92. There we go. All right, now, there's one other thing that we're going to need, just to make sure we get that now, is we need the N. We need the count, okay? And I forgot to get the count for population A, but you can see here that the count, that's the N, right? So the N for population B is 22, and the N for population A is, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So N is 16. And now we are done with the computer. We don't need Excel anymore for this problem. We have all the information that we need. Once we have this, so now we've done step 1. Calculate the variance of both samples. We have it. The larger variance is the numerator. This one is larger, so that means sample B is going to be the numerator. I'm going to write that in blue here. So this is the numerator. And sample A, which is the smaller variance, 77.9, that's the denominator. Okay, so we have that. Now, we have all the information that we need to start our hypothesis test. So after you've done that, step 2 is going to be to identify the null and alternative hypothesis. Let's just write here hypotheses. All right, so we're going to say H sub O is going to be the variance of A is equal to the variance of B. And the alternative hypothesis is that the variance of A is not equal to the variance of B. All right? And so now, step 3, we know that it's going to be a two-tailed test, so we're going to skip that step. Step 3 is state the alpha. So state the alpha and the p-value. Okay? So we know that we're going to, and the p-value is going to be equal to alpha divided by 2 every time. Okay? So for step 3, we're going to say alpha is the question said 0.10. So the alpha is 0.10, and so the p-value that we're going to deal with is 0.10 divided by 2, which is 0.05. Oops, that's not a good 5. 0.05. And what this means is that on your F table, which I put down around here somewhere, here it is, that on your F table, you are going to use the side that says F values for alpha equals 0.05. This is the side you're going to use. Do not use this side of the table or you'll get the wrong critical value. Okay? So that's step 3. Step 4, what kind of test? What kind of test and identify the degrees of freedom. Okay? So this is an F test because anytime, and I'm telling you right now, anytime you do a variance comparison test, it's always going to be an F test. Okay? So this is an F test, and F tests have 2 different kinds of degrees of freedom. We have the degrees of freedom for the numerator, and we have degrees of freedom for the denominator. Okay? And the degrees of freedom for the numerator and degrees of freedom for the denominator are, again, like before, like what we've learned before, they're n minus 1. And so, here, degrees of freedom for the numerator has an n of 22, and 22 minus 1 is 21. The denominator has an n of 16. 16 minus 1 is 15. And so now we have our degrees of freedom. We know it's an F test. We have our P. So now the next step, step 5, identify the critical F value. Okay, or F crit and the decision rule. And the decision rule. Now, here's the thing about F tests. F tests are always positive values. They're not negative values. Okay? So you're not going to ever have a decision rule where F is less than. It's always going to be F is greater than. So the decision rule is always going to be reject the null hypothesis if F is greater than a value. But let's look up our critical F value here. So F crit. Let's go into our F table. Degrees of freedom for the numerator is 21. That's across the top. And then degrees of freedom for the denominator, that's going to be along the side. Now notice across the top that it only goes up to 20. It goes 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 15, 20, 24, 30, right? So your rule is this, is if your degrees of freedom are not there, you should pick the next degrees of freedom down, okay? So we don't have 21, so we're going to select 20 as our degrees of freedom, and then along the side we're going to go to 15, okay? So when we go to 20 on the top, down, oh, I'm on the wrong side. I'm on the 0.01 side. Make sure you're on the right side. We got to be on the 0.05 side. So I'm going to go to 20 at the top, and I'm going to go down to where 15 is. If I go across 15, I get 2.33. So my critical F value is 2.33. And now my decision rule is reject H sub O if F is greater than 2.33. Okay? And now we're going to calculate the F value. All right? And the way, so now this is the part that you've probably been waiting for. You're like, what's my formula? What's my formula? It's actually a really easy formula. So calculate the F statistic. And here's the formula. F is equal to the sample variance of the numerator divided by the sample variance of the denominator. So all we're going to do is we're going to take the numerator variance and divide it by the denominator variance. So F is going to be equal to this number, 197.774892, 774,892 divided by 77.983333. That's it. It's just the variance, the larger variance divided by the smaller variance. So that's another way you can say, instead of numerator and denominator, you could just say large variance divided by small variance. And the reason it has to be large variance divided by small variance, if you did the smaller one divided by the larger one, the answer would always be less than 1. It would always be, and so if it's less than 1, it'll never be larger than 2.33. Your F value always has to be larger than 1. So it's always going to be larger variance divided by smaller variance. So if I grab a calculator here, I'm sure there's one right there. Let's grab a calculator. And so now I'm going to do 197.774892 divided by 77.983333, and I get 2.57. We're going to go to 2 decimal places here because the F crit is 2 decimal places. So we're going to go 2.54. And since this number is larger than this one, we are going to, and then make a decision. Make a decision. And in this case, because our 2.54 is larger than our critical value, we are going to reject H sub O. What is rejecting H sub O meaning? It means that we have statistical evidence that supports the idea that the variances are very different. And that's what we're looking for. Okay? Let's do another example. All right, here's another one. And it says, determine whether the variances of the 2 populations are significantly different at the alpha equals 0.02 level. And here's population A, and here's population B. Why don't you go ahead and pause the video and use your computer and find the variance of population A, then find the variance of population B, and determine which one should be the numerator and which one should be the denominator. Then we'll go ahead and work it through together. All right, so let me go ahead and find the variances of these two samples. So I'm going to take population A. I'm going to bring it over here to the side, maybe. Sorry, I'm zooming out here. Let's put it right here. And I'll put this here. I'm going to put them in one column, which is how I want them. And then, once they're in one column, now I can go to data and data analysis. I can select Descriptive Statistics, select OK. I'll select my input range between this 9 and this 7, press Enter. I'll select an output location, maybe right here, Enter. Select Summary Statistics and click OK. I'm going to increase the size of the font there, and we can see there's the sample variance right there. Right here, I'm not sure how well you can see this, but it says 13.86666. It's a whole bunch of sixes. So, and the count for population A is 16. So for population A, N is 16, and the variance, okay, so the variance is 13.8666. That's pretty good. All right, well, I guess I could make it a 7. For those of y'all who are freaking out, you just said 666. It's 8.8667. Okay, now let's do the variance for population B. All right, so let's see here. We'll move over here. Let's delete this. And we'll grab population B. And we'll copy that, bring it down here. And I'll put it into a single column. There we go. So far, so good. X and here. Let's delete this. Put a new one in. All right, so this is population B, or the sample from population B. We're going to go data analysis, descriptive statistics. We're going to pick a new input range. We're going to go from this 5 down to this 10. And then we're going to pick a new output range. We'll pick, pick the same one probably. Enter. select Summary Statistics. We'll hit OK, and we're going to increase the font there so we can see it better. It says Sample Variance. Let's make it a little bit bigger there. Sample variance is 4.525. Oh, it's overlapping here. Sorry about that. Variance 4.5256. So population B. And the count is down here. It says 13. So N is 13. And then the sample variance for population B is 4.5256. All right, good. And that's all the information that we need out of the computer to be able to do the rest of this. So I'm going to get rid of this information here. And now we can follow our procedure. This variance, population A has a larger variance. Therefore, that's the numerator. Population B has a smaller variance, so that's the denominator. And the degrees of freedom for the numerator, is 16 minus 1, so that's 15. And the degrees of freedom for the denominator is 13 minus 1, so that's 12. So numerator degrees of freedom is 15, denominator degrees of freedom is 12. And our alpha, which was given us, is 0.02. So let's go ahead and start doing all our procedure here. What's the hypothesis? Well, the null hypothesis is the same every time, or at least in this class it is that the variance, that's not a very good sigma, hang on, is that the variance of population A is equal to the variance of population B. No difference in the variance, same variance, right? But the alternative hypothesis is we suspect that these two populations have different variances. Okay, well then that's our alternative hypothesis. Step 3, state the alpha. Well, we were told in this question that the alpha was 0.02. And since it's a two-tail test, remember, whenever we do a not equal to, that's a two-tail test, we are going to do 0.02 divided by 2. So the P is 0.01. Also, it's an F test, and the degrees of freedom for the numerator are 15. And the degrees of freedom for the denominator are 12. So we are going to use this 0.01, the degrees of freedom 15, numerator, degrees of freedom denominator 12. We're going to go to the F table, and we're going to make sure that we're on the side of the F table that says 0.01. 0.01, right? And on this side, we're going to go to a numerator degrees of freedom is 15, so we're going to go over to the 15, which is right there. And we're going to go down to the degrees of freedom 12, and it says that our critical value is 4.01. I see 4.01. All right, so F crit is 4.01, and so our decision rule is reject H sub O if F is greater than 4.01. So now last step, we just need to calculate the F statistic. And the way we calculate it is we do the larger variance divided by the smaller variance. Okay, well the larger variance is 13.8667 divided by the smaller variance is 4.5256. And I'll grab a calculator and plug that in. 13.8667 divided by 4.5256, and I get 3.06. Note, that's a good F right there, 3.06. A lot of times that'll give us significance, right? Except we're comparing it to 4.01. 3.06 is not larger than 4.01, so we are going to say do not reject H sub O. We do not have sufficient evidence to suggest that the variances are different. You're going to say, Mr. Ryan, one of them's like 14, the other one's like 5. You're telling me they're not different? I'm telling you that there is not statistical evidence to conclude that there is a significant difference between the variances. That's what I'm telling you. okay? You can fight with the test all you want to, but if you change your answer because you don't like the way that this is being done, then that's not how science is done. You need to stick to the rules of science, okay? In order for your conclusions to be acceptable in the scientific community, you got to follow the rules of statistics, okay? You don't get to make up the rules for statistics. Now, you can, if you want to go into the area of statistics and make up your own rules, make up your own tests, that's fine. That's great. We need lots of people to do that sort of thing. But you can't take existing statistical techniques and just say, oh, well, I don't like that, so then it's wrong and I'm right. It just doesn't work like that, okay? So let's do one more example and we should be good to go. All right, here's one more example. It says, determine whether the variances of the two populations are significantly different at the alpha equals 0.02 level. Here's population A, population B. Well, it's not population, it's the sample from population A. This is the sample from population B. You can see we got a much smaller sample from population B than we did from population A. That happens sometimes, okay? So here's what you need to do is step one, you need to calculate the variances of both samples, identify one of them as the numerator, identify the other one as the denominator. Don't forget to identify the degrees of freedom for each one as well. Go. Okay, so now I'm going to go ahead and do it. So we're going to go over here. I'm going to zoom out a little bit here. Grab these numbers. Let's do population A. Put it right here. Let's grab that. And I'll put it here. Just trying to put them all in one column because you know we got to put them in a column to be able to do the descriptive statistics, right? So I'm putting them in a column so I can do the descriptive statistics. This is the larger one, so it's going to take me, you know, about a minute. Here we go. Okay, good. Now I'm going to go here. I'm going to go to data, then data analysis. I'm going to choose descriptive statistics. I'm going to choose an input range, which is the column of all the sample observations from population A. And then I'm going to, I chose summary statistics. I need an output. That's a good output right there. And then I'm going to hit OK, and there are my summary statistics. Let me blow that up a little bit so that we can see it. All right. Oh, there we go. Look at that. Sample variance. Here it is. 7.9057. Is that it right here? All right. So this is population A. Has a count of 24. So our sample size for A is 24. And then our variance, S squared, for population A is 7.9058. 7.9058. Okay, now let's do population B. Should be a little bit faster. Let's go ahead and delete this. And we'll delete this. And let's come over. Oh, I accidentally took away population A. That's okay. We'll copy this. There we go. It's only 10 numbers here. Shouldn't take as long. But just put them all in one column because they got to be all in one column. You had to type them in. I can copy and paste, but you got to type them in to Excel. All right, let's grab this, put it up here. There we go. Okay. Now I'm going to go to data, data analysis. I'm going to choose descriptive statistics. I am going to select these 10 numbers, press enter. I'm going to choose my output range. I'll keep it in the same place. Summary statistics, hit OK. I'm going to increase the size of the font there. And you can see, whoops, a little bit bigger there. There we go. There's the sample variance. So for population B, you can see that the sample size, the count is 10. So for population B, N, sample size is 10. And the variance is 34. All right. So variance for population B is 34.9444. There we go. And that's all the information that we need from the computer, so we can turn this off. Okay, and now we can go ahead and do our procedure. Now, which one is the numerator? The larger variance is the numerator. That's just 34 here, right? That's the numerator. And the denominator is the smaller variance. That's this one. So this is the denominator. And the degrees of freedom for the denominator, degrees of freedom here is 24 minus 1, that's 23. The degrees of freedom for the numerator, 10 minus 1, that's 9. Okay? And now let's go to step 2. Let's do our hypotheses, our null hypothesis. The variance of population A is equal to the variance of population B. And the alternative hypothesis is that the variance of population A is not equal to the variance of population B. Okay? And the next step, state the alpha. The question said that the alpha is 0.02. And so for the p-value, because it's a two-tailed test, we're going to do 0.02 divided by 2, which gives us 0.01. All right, so 0.01. What kind of test is this? Well, whenever we do the two-sample variance comparison, whenever we compare the variances, that's an F test. And what are the degrees of freedom? Well, the degrees of freedom for the numerator is 9, and the degrees of freedom for the denominator is 23. So, with a 0.01, numerator degrees of freedom 9, denominator degrees of freedom 23, we can now go to our F table. Let's find our F table. Make sure that we're on the side that says 0.01. So 0.01, all right, and now we're going to look for degrees of freedom, numerator 9, degrees of freedom, denominator, all the way down here to, where's 23? Somewhere around here. 23, there it is. I'm looking at it backwards. All right, so 9, 23, I'm coming up with 3.30. 3.30. So our critical F value, F crit, is 3.30. So our decision rule is reject H sub O if F is larger than 3.30. Now we're going to calculate the F value. So to calculate the F statistic, we're going to do the larger variance, which is 34.9444, divided by the smaller variance, 7.9058. Grab a calculator. Go. And we're going to do 0.9444 divided by 7.9058, and I get 4.42. 4.42, which is larger than 3.3, so our decision is reject. Reject H sub O. Okay? And this is this is evidence to indicate that the variances of population A and population B are very, very different. Okay? Well, that's all I have for you. Make sure you do all the problems that I give you. Don't forget to take the quiz. Hopefully this will help you a little bit. I do want to give you a sort of a side note, is that this test is in the textbook that I primarily use as a reference, but it is not in, there's sort of a book that you can buy at the bookstore that helps you understand statistics, like Statistics for Dummies or something like that, that this test was not in that book. And so this test is probably one that's not used as frequently as some of the other tests. The one we're going to use in our next video, that is a very, very popular common test. And in that, for the next thing we're going to learn, you are actually going to need your Excel. Excel is going to do all the work for us completely. We're not even going to use the F table for that particular one. We're going to let Excel tell us what the critical F value is. But for today, hopefully you got a hang of this, you got your procedure written down, and you should be good to go.